Good day and welcome to Math 111H Calculus 1 Honors, The Joys of X. Today we'll discuss definite integrals. Here's the definition. If we have a continuous function f on an interval from a to b, and we divide that interval into subintervals and take sample points in each subinterval with the function value being f at x1, f at x2, etc., and the width of each interval being b minus a over the number of subintervals, what we get is an approximation to the area under the curve using rectangles. We take narrow rectangles, and then the definite integral from f from a to b is defined to be the limit as we take the number of rectangles to go to infinity of the function value somewhere in each rectangle times the width of the rectangle. So we're getting the area under a curve, at least for a positive function. If the function has negative pieces, these pieces will be negative. We'll call those negative areas. This limit exists, and it won't depend on the choice of the point in each interval. So what we're saying is that if we divide an interval up into tiny pieces and we consider the area under the curve as being approximated by rectangles in those subintervals, we can add up the areas of those rectangles, and in the limit, as the number of rectangles goes to infinity, we get the area under the curve, or the definite integral. Some of the properties of definite integrals are: if the function is always positive on the interval, then the integral is simply the area under the curve. If the function takes on both positive and negative values on the interval, then we get what we call the net area. The area below the x-axis is taken to be a negative area. So we get a net area, the positive area above the axis, and we would subtract the area below the x-axis. Here are some areas you should know because you know about certain shapes. If we consider the integral, the area under the curve, from 0 to 1, of the square root of 1 minus x squared dx, what do we have there? Well, the function y equals square root of 1 minus x squared, that's a semicircle. And the integral from 0 to 1, that's simply the quarter circle. So since the area of a circle is pi r squared, that would be pi times 1. The area given, or the integral from 0 to 1 of the square root of 1 minus x squared dx is going to be 1/4 of pi over 4. We can also consider the area under the curve x minus 1 from 0 to 3. Well, what does that curve look like? It's simply a line. And from 0 to 3, we end up with a negative area from 0 to 1. 1/2 base times height gives us negative 1/2 for this area. And the positive area from 1 to 3, we have a base of 2, a height of 2. 1/2 base times height is 2. So the integral is going to be 2 minus a half, or 3/2. Here are some of the properties of definite integrals. We consider the integral from a to a of f of x dx. That's going to be 0. So for example, here we have a curve and we take the integral from -3 to -3. Well, the width of that region is 0. So you have 0 times the height gives you 0. If, on the other hand, we had the function f of x as a constant, we have the integral of a constant from a to b is simply the value of the constant times the width of the interval, or the area of a rectangle. In this case, the height is 5, the width is 4, and the area is 20. We also have the following properties. The integral from a to b of f of x plus g of x is going to be the integral of f of x plus the integral of g of x. That these areas can be added. If we multiply f of x by a constant c, then the area under the curve is simply c times the area under f of x from a to b. And if we take the integral from b to a going backwards instead of from a to b, our dx, or our delta x, is really becoming negative. It's going from right to left. So we get that area as being minus the area from a to b of f of x. If we go backwards, we get minus of the integral. Some more properties of definite integrals are: if the function is positive on a to b, then the integral will also be positive because the area will be positive. If f of x is bigger than g of x, then we can subtract f of x minus g of x is then positive. And so we have the integral from a to b of f of x minus g of x is the integral of a positive quantity, and that's got to be greater than 0 if b is greater than a. and therefore we can bring to the other side the integral from a to b of g of x, and we find that if f of x is bigger than g of x, then the integral of f of x dx is bigger than the integral of g of x dx. Finally, if f of x lies between little m and big M, meaning that the function is greater than little m at all points on the interval, and it's less than big M at all points on the interval, well, we know the integral of m from a to b is simply m times b minus a. The integral of big M on the interval from a to b is big M times b minus a. And since f of x lies in the middle everywhere on the interval, that the integral of f of x dx from a to b must lie between m times b minus a, little m times b minus a, and big M times b minus a. Let's take a moment for math culture. There was once a math professor who was quite absent-minded. And when his family moved from Cambridge to Newton, his wife, knowing that he would be absolutely useless on the move, packed him off to the university while she directed the move. She was certain that he would forget that they had moved that day and where they had moved to, so she wrote down the new address on a piece of paper and gave it to the math professor. Naturally, in the course of the day, an insight occurred to the math professor. He reached into his pocket, found the piece of paper, and he scribbled furiously some notes. He thought it over and decided there was a fallacy in his idea, crumpled up the paper, and threw it away. At the end of the day, of course, he went home to his old address in Cambridge. When he got there, he realized that his family had moved because my family's not there. And he had no idea where they had moved to because the piece of paper with the address on it was long gone. Fortunately, inspiration struck. There was a young girl on the street, and he conceived the idea of asking her where he might have moved to, saying, "Excuse me, young lady, do you know perhaps the professor that used to live here? I'm that professor, and we've just moved. Do you happen to know where we've moved to?" To which the young girl then replied, "Yes, Daddy, Mommy thought you might forget. I could take you home now." Thank you for joining us today. Have a great day, and may the power of math be with you.